Hello guys, welcome to Coding. In this video, we are going to see the Leetcode problem number 279 perfect squares. Let's get into the problem. So the problem statement is, you'll be given an integer n, you need to return the least number of perfect squares that sum up to n. So a perfect square is nothing but an integer that is square of an integer. So in other words, an integer which is product of some other integer. So for example, 1, 4, 9 and 16 are perfect squares while 3 and 17 are not. So let's get under the problem definition. So before moving on to solving the problem, we need to define the problem clearly. So first step is to define the problem. So what is the input? So input is nothing but an integer n and output is minimum number of perfect squares, let's call it as PS, that sum up to n. So this is the input and output. So what is the perfect square? So perfect square is nothing but an integer which is product of an integer itself. So other integer, the whole square, I mean the square. So for example, one let's say 1, 4, 9, 16, 25, 36, 49, etc. It goes on. So 1 is the perfect square of number 1, and 4 is the perfect square of number 2, 3, 4, and it goes on, 5, and it goes on. So this is all about the perfect square and input and output. So n can have values between 1 to 10 to the power 4. These are stated in the question. And yeah, any other points to be noted from this question. So yeah, this is all about the problem definition. Now let's move on to approach of this solution. I mean approach of this problem. So the second step is nothing but approach. So how are we going to approach the problem? So they are given an integer n, right? So any integer can have sum of perfect square because there is one. So we'll add up one till we get the n. So it will be n. So this is the one possibility. So for any integer n can be sum of any two. So we'll consider just two integers a and b. So when we consider and any integers to a and b, that leads to some n. So consider the number 1. So 1 can be the number of perfect square that can number of possible ways for adding two digits to get some 1 is 0 plus 1. So this is the only possible way. So consider 2. So 2 can have values like 0 plus 2 and 1 plus 1. So 3 can have some like 0 plus 3, 1 plus 2. Yeah, that's it. So 4 can have values like 0 plus 4, 1 plus 3, 2 plus 2. So these are the possible combination for 4, and it goes on up to infinity. So for each value, we're going to represent the number in sum of two numbers. So yeah, initially, so for solving n, so in order to find the answer for n, we need to find the values from 1 to n. So we'll use a DP approach. So dynamic programming approach can be applied to this problem, since we can just calculate the sum of perfect square required for the given two numbers. So consider, let's say, for 1, the number of perfect square is required is 1, and for 2, number of perfect square is 3, required is 3 because 1 plus 1. So for 3, the number of perfect square is 3 because 1 plus 1 plus 1 is the minimum. So this is the n and the minimum perfect square, minimum number of perfect squares. So for 4, 1 because we'll just use the 4. So for 5, the number of perfect square required is 2, that is 4 plus 1. And for 6, the number of perfect square is 3, so it's nothing but 5 plus 1. So 5 plus 1 is nothing but 4 plus 1 plus 1 is the minimum, and for 7 it's nothing but 4. So 4 plus 1 plus 1 plus 1. So these 4 perfect squares are required to sum up 7. And for 8 we have 2, which is 4 plus 4. So it goes on. So how can we find the answer for each value? So we can find the answer for each number by using two sum of previous squares. So consider 1. So we'll have default of value of 1, answer 1 for 1 as 1, and for 2 we'll just use uh, 2. For 3, what we can do is we'll have sum of two numbers. So consider 3 can have sums like, as we have discussed, 3 can have sum like 1 plus 2. We'll ignore this first case and we'll just concentrate on other ways to add up to 3. So for 3, we can add 1 and 2 to get 3. So this is the only possible way. So from this we can clearly see that 3 can have 1 plus 2, which is 3. So why we are having 3? That is nothing but 1 plus 2 is the combination for 3. So number of perfect squares needed to build up 1 is 1. The number of perfect squares needed to build up 2 is 2. So we are just adding these values. So what step we are doing is, we are doing nothing but we are choosing the A and B. That is two sum. These are the two sum. So A and B, and we are just adding up the values and storing it in the answer. So this is the step we are going to do for each integer. So let's consider the number 4. So since 4 is a perfect square, we'll just have it as 1. So for perfect squares, we'll store the value as 1, and for other numbers, we'll find the combination and take the minimum. So for 5, what we'll do is check for all possibilities. So 1 plus 4 is 5. So the value is nothing. We'll add up the value. So 1 plus 1 is 2. So we'll store it and we'll check. We'll not just stop over there, but we'll check over other possibility. That is 2 plus 3 is also 5, and we'll add up the values. That is 2, 1, 3, and 2 plus 3 is 5. So 5 is greater than 2. So we'll leave it as it is. So we'll stop the iteration and move on to 6. So for number 6, we have many possibilities like 1 plus 5 is 6. So we'll add up the number of perfect square needed to build up 1 and 5. So 1 is 1 and 2 is 5 is 2, so answer will be 3. So 3. So what step we are following here is, first step we are taking a number and choose the first step is choose two sums, two integers that sum up to n, that sums to n. So for each n, so let's say yeah, for each number we are going to choose two integers that sums to a number. This is the first step, and the second step is we are, for each time when we choose the two numbers, we are adding the number of perfect square needed. So let's say we are choosing integers a and b. So what we'll do is we'll just add the number of perfect square for a and number of perfect square for b, and store it in the store the minimum value. So we'll store this value in the uh, numbers number of perfect square. So the first step is choose integer, and second step is add the number of perfect squares. So let's say we have 7. So for 7 we have many possibilities, like we first need to choose the values. So 6 plus 1 is 7, 2 plus 5 is 7. So before moving on to next, firstly we have 1 and 6. 1 plus 6 is 7. So we'll add up the value. So 1 plus 3 is 4. So store the 4, and we'll check the other possibilities. 2 plus 5 is 7, and the values are 2 and 2. So 2 plus 2 is 4, but already we have 4, which is the minimum value. So we'll continue. So 3 plus 4 is also 7, and the values are 3 plus 1, which is 4. So 4 is equal to already founded value. So we'll start it. So 4 is the required answer for 7. So when we consider for 8, we have possibilities like 1 plus 7. So 1 plus 7 is 8, and we'll add up the values. So initially, let's say we have max value for 8. So we'll add up 1 and 4, 1 and 7, which leads to 8, and we'll find the number of perfect squares for 1 and number of perfect squares for 7. So it's nothing but 1 plus 4, which is 5. So 5 is less than max value, so we'll store 5. So we'll continue on. So 2 plus 6 is 8. So 2 and 3 sum will lead to 5. So 5 is already found. So it is not less than already found value. So we'll move on to next, which is 3 plus 5. 3 plus 5 is 8, and the sum of values are nothing but 3 plus 2 is 5. So it's not less than already found answer. So we'll move on to next value. So this is the condition in where both the pointers point to same value. So 4 plus 4 is 8, and 4 plus 4 is 8. So we'll add up the values. So 1 plus 1 is nothing but 2. So 2 is less than 5, so we'll add up 2. So this is the steps we are going to use for this problem. So when we consider this, the time complexity, so we'll it's look messy, so we'll delete this up. So when we consider this approach, uh, or the time complexity will be we go of n into n by 2, since for each time we'll be moving one digit. So n will be for since we for the outer loop, which will be running from 1 to n, and the next n by 2 is for nothing but firstly we'll have a j pointer j, which will store the like 1, and we'll have a k pointer which will store n minus 1. So for each time we'll increment the j will be incremented and k will be decremented. So for each time we'll if I have, let's say we have created an answer dp. So while j less than k, less than equal to k, we'll have dp of I is equal to min of already calculated value. So initially we'll have dp of I as max value. So dp of I comma uh, dp of j plus dp of k, and we'll decrement the j, sorry, we'll increment the j and decrement the k. So this is the logic, this is the complete solution for this problem. So what we have done, uh, we have followed the same steps. It's nothing but we are going to iterate from 1 to n. So 1 to n, we are iterating over 1 to n. So for each time we are having two pointers, that is first pointer will be 1 and the next pointer will be n minus 1. So sorry, it should be I minus 1, I minus 1. So before this condition we'll check whether the if I is perfect square. If perfect square of I, what we'll do is we'll just have the value of I as 1. So why? It's nothing but perfect square like 1, 4, 9 can be built up with just one perfect square, right? So answer of all of this will be 1. So we are having this as a base condition and we are using it here. So this is the base condition, and these are the other condition. So we are nothing doing nothing but we are having j in 1 and k in I minus 1. So current value minus 1, let's say for value 13, it's not a perfect square, so we'll come into this condition. So in this what we'll do is j will be 1 and k will be I, this I is 13, so k will be 12. So initially we have chosen 1 and 12. So we'll find the minimum, that is the sum of answer of dp of 1 and 12. So dp of each value is nothing but number of perfect squares required to uh, sum up to the number. So initially we'll have this, and next we'll increment the j to next value. So and decrement the k 11. So 2 plus 11 is 13, and we'll find the sum of minimum perfect square required for 2 and 8, and for each time we'll store the min value. So finally we'll be able to calculate the minimum number of perfect squares required to sum up to 13, and we'll store this in the cell dp of 13. So we'll be storing the each value. So dp of any value, dp of I will have minimum number of perfect squares that sums to I. So this is the statement of dp. So after this operation we'll just return the dp of n, dp of n. So this is nothing but the minimum number of perfect squares required to sum up to n. So this is the logic behind this approach. This is considered to be the first approach. So the time complexity becomes big of n square. So can we reduce this time complexity? And the answer is yes. And how? So we'll have the outer while loop, outer for loop as it is, and we are going to have alterations in the inner while loop. So what we are going to do? So we are nothing. We are going to do like let's say we have number 13. So each time we'll reduce the number by squares. So 1 plus, so we'll have one perfect square and the other will be the remaining part. So initially we'll have 1. So 1 minus 13 will be 12. So we'll find this answer and we'll store it in the minimum value. And next possibility is nothing but we have chosen one. So square numbers. So initially we have 3, 4, 5, etc. Right? So these are the numbers. So what we'll do is firstly we have taken one square and the remaining of we'll take the one and square it up and we'll reduce from 13, which will get us to 12. So we'll find the perfect square of only this case. So we are not going to check for every cases like 1 plus 12, 2 plus 11, etc. So yeah, after finding for 1, what we'll do is we'll go to 2. So 2 square is nothing but 4 and the remaining part of 4 is nothing but 4 plus 9. So 4 plus 9 is 12, 13. So we'll find the number of perfect square needed for building up this. So again we'll move on to 3. So 3 is nothing but the same value will be repeated. So 9 plus 4, which we have already found out. So we'll stop the iteration. So when the number becomes greater, repetitive, we'll stop the iteration. So if you're not clear, I'll give you other example. So consider the number 17. So 17. So before that, we have numbers 1, 2, 3, 4. So 17 will have one perfect square and the remaining value. So initially we'll choose. So perfect squares will have the perfect square values. So the perfect square is nothing but 1, 4, 9, 16, right? So we'll have the perfect square. So it goes on. It's not limited. So firstly we'll choose 1. So firstly 1 plus we are choosing the perfect square and what is the remaining value? It's nothing but 16. So we'll find out this value and store it in dp of 17. So initially it will be maximum value. So when we find this, we'll update the max value and move on to next value, which is 4. So for 4, we'll use like 4 plus. What will be the remaining of required value to sum to 17? It's nothing but 17 minus 4, which is 13. So we'll find this value and update the minimum of both values, pre-calculated value, and we'll move to 9. So when we choose 9, the remaining value will be 8. So 17 minus 9 is 8, right? So we'll take the value and compare with the dp of 8. So what value we are taking is nothing but dp of 9 and dp of 8. So yeah, and we'll move on to next, which is 16. So 16 is summed up with 1 to get 17. So we'll find the value of 16 and 1, that is the dp of 16 and dp of 1, and we'll compare with the value and we'll move on to next number. So 25. So 25 is greater than the chosen number, so we'll stop the iteration. So this is the step we are going to use. So we are reducing this while loop into So this has a time complexity of n by 2. So we are reducing it by square root of 2. So this is all about this approach. This is the approach number 2. So the time complexity will be big O of n into square root of n. So this is the time complexity. So if you are not clear about the solution, you will be very clear in the coding section. So let's move on to coding section. So initially we'll have dp array int of n plus 1. So for in I is equal to 1 and I less than equal to n I plus plus. So if current number I is square, we'll store dp of I as 1, or else we'll continue, or else what we'll do is we'll have current square as 1. So we have current num, so let's call it as num. Current num is 1. So while current num square is less than n, less than I, what we'll do is, so this is nothing but the perfect square. So for 1 2 we'll be moving on this time. So we'll check, we'll have the, for initially I will have the dp value of I as max value, which integer dot max value. So dp of I is nothing but max dot min of dp of I, so pre-calculated value, and dp of, so we'll find the, this is considered to be a value a. So a is nothing but current num into current num, and b is nothing but I minus current num, so remaining number. So yeah, as we have mentioned, so when we consider the number 17 and we have chosen 4, when we chose 4, what will be the remaining value? So 4 plus remaining number, so the remaining number is nothing but 13. So we need to find this number. So in order to do that, we'll take the I, this is I, and this is the perfect square, right? So we'll subtract I minus I by perfect square, I minus 4. So this is the same we are going to use here. So I minus a, and we are adding the dp of a and dp of b, and we'll increment the number, and finally we'll return the dv of n. So we'll write the helper function, where boolean is square. So it will get the integer n, and it will find the square root. So let's say square root is nothing but math dot square root of n. So it will return a double value, will convert it into int value. So we will return whether square root into square root is equal to n. So this will help us to find whether the current number n is a square number, a perfect square or not. So this is the solution behind this. So firstly we are creating the array, and if it is square we are updating it to 1, and we are having a current number as 1, and we are having storing the max value as the uh, number of perfect squares required, and we are iterating over the complete square root times of I, and updating the max value dp value. So let's check it out. So It's working fine. So let's submit it up. Yeah, accepted. And as I discussed, the time complexity of the approach is O of n into square root of n. Let's say sqrt of n. And the space complexity is nothing but U of n, since U is a DP array of space n plus 1. And the approach for this problem is mathematics and dynamic programming. So that's all about this video, guys. Thanks for watching this. Have a great day.